Hello everyone, and welcome to Understanding Physics, in which I will try to guide you into understanding physics and getting the main concepts into your mind. So, in General Physics 1, we want to talk about the motion in a straight line, which is the basis for kinematics, or the study of which is the study of how you model things to move. So, to do kinematics, you need to know certain things, such as position. Position is where you are located at. So, for example, let's say this is 0. You could say that your position will be at a certain distance from 0, or your point of reference, which is, for example, in here to be x. So, after this, we want to discuss about the difference between distance and displacement. The way that you could discuss this is that distance is how far you move, while displacement is how much change of position you have moved. So, let's say, for example, if you move from one point to another point, and then you go back to a third point, the distance is from here to here. While for the displacement, you go from A to B to C, it is like going from A to C straight away. And that's the difference between distance and displacement. So, the way that you would actually describe this is that you could say that you need to add the distance from A to B added up by the distance from B to C. While displacement, you need to deal with vectors, which will later be discussed on the next chapter. So, we want to also differentiate between speed and velocity. Well, in this case, we want to do average speed and average velocity first. So, for the average speed, you would use distance over time, which will be a scalar, the same as for distance to be scalar, while velocity is displacement over time, or you could write it as delta S over delta T, and this is a vector. So basically this means that if you move in the other direction, your velocity will be the negative sign of that, which is one of the key parts in understanding physics. You need to know which ones are scalars and which ones are vectors. So, after you have figured this out, or yeah, you could basically write this guy as delta x, which is the same thing. So, the way that you start doing a kinematics problem is that you need to first try to define where your origin is, because through this origin you could find out the position, and then through the position you could figure out the displacement or the distance depending on the use that you need. So we have talked about the average speed and velocity, but we could also talk about the instantaneous velocity. And what is that? So, let's say if you actually measure the average velocity but with a smaller amount of time. So let's say, for example, if you are moving with a different rate, let's say at the initial you moved with a very large velocity compared to your final state, and then we try to keep track of it. No, sorry, let's just draw it like this. Let's say you move from one point to another, like this. Let's see if I can draw it perfectly. So each line tells you about a certain unit of time, let's say. So within this certain unit of time, let's say from here to here, you would have moved from delta s to delta t. But then, like, if you start to shorten out the time, your delta s will be smaller, but then your delta t would also be smaller. And if you do this until delta t is very small, you would get a term in mathematics which we call limit, in which if you set the delta t, the change of time, to be nearer and nearer to zero, or something very small, of the average velocity, you would get a number that is like very close, as if you are measuring the speed during that certain point. And this is how you actually read speedometer. Well, actually a speedometer reads the average, no, sorry, the instantaneous speed. But we could actually interpret it as the instantaneous velocity because we know its direction as well. And this could also be written as dx over dt, which is the way that we write it in terms of a derivative. So if you don't know about derivatives yet, I hope that you will try to understand the derivatives first. So we have already discussed about the instantaneous velocity. So we can also do the same thing with something that we call as the acceleration. So the acceleration is basically the change of velocity over the change of time. And this is what we call as the average acceleration. And by the way that we write these in mathematical form is that you could write the average velocity to be v bar and this to be v. So the average acceleration could be written as a bar, and while the instantaneous acceleration, or you could call it as the acceleration, will be the limit when delta t goes to 0 of the delta v over delta t, which is basically almost the same thing as you do with position. And this could be written as the dv over the dt. And if you substitute the v, you would be able to obtain the d squared x over dt squared, or basically the second derivative of your position. So you have figured out the entire way of you trying to figure out what is the instantaneous velocity or the instantaneous acceleration. So we want to study a very interesting case of kinematics, which is during a constant acceleration. So what you would know is that a is dv over dt, and this a is a constant, or you could say that to be as a number. So if you have taken differential equations, you could write this as a dt to be equal to dv. And if you would integrate this over the initial towards the final, or you could write this as t0 and t of a dt, and it equals to the integral from the initial to the final, or the velocity, dv, you would have got a t minus t0, which equals to v over v0. Normally as physicists, we normally consider t0 to be 0, as it is one of the simplest case. But if it is not 0, you could just use a linear transformation to actually shift your time frame. So continuing this on, you can get your velocity to be v0 plus a times the time, the acceleration multiplied by the time. And if you check the units, this would have made sense, since acceleration would be meter per second squared multiplied that by time, which is seconds, and velocity is meter per second. so it would make sense. So after that, you can determine what the position is because velocity is the change of position over the change of time. So the way that you would actually solve this is the same way. The dx would equal to v0 plus at dt. And if you do the same integration, you could get the final minus the initial, which equals to the integration, which is the integral from 0 to time, or basically this to be times 0 of v0t, the v0 plus at dt. And if you take the integral of this, you would obtain this to be v0t plus a over 2t squared, since v0 is a constant and a is a constant, and the integral of t is t squared over 2. And also, if you do the evaluation, instead you would have the minus 0 on the end. And so you would be able to obtain this equation, or normally we write it as x equal to x0 v0t plus x0 plus v0t plus a over 2t squared. And so this is one of the equations for you to actually determine what's the position if you know the initial acceleration as well as the initial velocity for a constant acceleration type of motion. But there is also one equation which can be used to figure out the velocity or position, but you don't know the time. And the way that you would be able to obtain this is from this first equation. You could be able to obtain the time to be the v minus v0 over a. So this equation tells you at which point in time you would be able to get this certain velocity. And if you substitute this value here, you would be able to get x0 plus v0 multiply that by v minus v0 over a plus the a over 2 v minus v0 over a squared. And so this seems to be a little bit weird to write, so we should try to figure out a way to write this in a much more proper way. So I will just first put x minus x0 on the left hand side, and then we could write the right hand side as v0 with v minus v0 over a plus 1 over 2 a v minus v0 squared. So this seems better, and let's just multiply the right and the left hand by 2a. So we would be able to obtain 2a x minus x0 to be equal to 2v0 v minus v0 plus, and let's expand this straight away, v squared minus 2v times v0 plus v0 squared. Okay, this seems reasonable. So you would be able to obtain 2x minus x0 to be equal to v squared, and then 2v0 times v, subtract that by 2v times v0 would be 0, and negative 2v0 squared plus v0 squared would be negative v0 squared. And this is one of the core equations that you could use to find a certain velocity at a certain position, or the other way around. So there are about 3 important equations that you need to know, which is v equals to v0 plus at, x equals to x0 plus v0 plus a over 2 squared over a over 2t squared, and v squared minus v0 squared, which equals to 2ax minus x0. And so you could actually use this equation not only to determine something that moves horizontally, but also something vertically. As you know, as there is a way for you to figure out the acceleration of gravity to be a constant. So gravity, so there is something that we call as the gravitational acceleration, which we normally denote as g, which equals to about 9.8 meters per second squared. But sometimes people use 10 meters per second squared since it is a much more reasonable number to manipulate if you do the calculation on top of your head. And the way that you would be able to obtain this gravitational acceleration is through the Newton's law of gravity. And if you do that within near Earth's surface, you would be able to get a constant about 9.8 meters per second squared, although that the gravitational acceleration would depend on the height. But in here, the height doesn't truly matter because it is very small compared to the radius of the Earth. So, you could just put the gravitational acceleration into your acceleration to figure out your values. But there's something that we didn't discuss, which is we should also try to discuss if the acceleration is changing. So if you have a changing acceleration, the way that you would actually discover its position and velocity is through calculus. So if you have not realized it or not, previously I used calculus to derive the equations for a constant acceleration. But you could also do this with a acceleration which is changing over time or even position. So you could write the velocity to be the integral of the acceleration over the time, while the position could be written as the integral of the velocity over time. And so this is one of the importance of you trying to understand mathematics first, is that after you could do the mathematics, you could do almost any different physical systems as long as you know the equations. So we have already discussed about the entire formulas that we need to describe kinematics within one dimension. So there is a example question that I will give, which is, if you are in a car there and you're moving at pretty much about 25 meters per second, and then during a certain time, let's say in here, you discover there is a hazard about 60 meters away from the place that you have realized this. And so you try to hit the brake. And so the question is, how much acceleration do you need to stop before this point? And this is not a simple question to discuss, but this is the best way for you to actually to understand the physics in kinematics and how it is used. So let's just actually start with a simple question first, which is, in here, let's just state this to be time equals to 0. And let's just use a very borderline condition in which it will stop exactly at the hazard. So we could just describe this using one of the equation, which is v squared minus v0 squared to be equal to 2a of x minus x0. And let's just state that at time is 0, the x would be 0. So let's just use the x0 here to be 0 and the x to be 60. And let's use v0 to be 25 meters per second squared, while the final velocity in which it must to stop, therefore its velocity must be 0. And let's figure out how much acceleration do we need. So, doing the computation, you would be able to get 625 over 120 in the negative direction, which basically means that it is going in the opposite direction compared to the speed of the car. So, you would need about this much deceleration basically. And so, let's just hope that your car could actually stop with the friction that it has, so that it would stop right here or before it. So therefore, the deceleration should be more than 625 over 120, or you could actually simplify this to be 125 over 24, which is about 5 point something. So this is our system in which we want to try to model. And so in here I have already set it up a Desmos simulation. So in here, let's just start from time to be all the way back. And let's say it will later hit this 0 point. So if we just let it run, let's say here to be -2. So during time to be -2, this car will move, and then it will just try to decelerate until the 60 mark. And yes, I use 5.2 here to actually predict where it will later stop. So if we set up our deceleration to be more than less than 5.2, we will just crash into this hazard and stop at a point further than 60, which is a bad cause, which means that we have crashed. But if we go over it, let's say if we go until 6, and let's just put this to be 25 over 8, we would be able to stop before it hits this point. So we could actually model this into a function of time as well as position. So in here I have modeled its deceleration. So you could see if I actually decrease the acceleration, that means that I am setting its height to be much more nearer to 0. While if I actually set it up to be higher than 10, that means that its deceleration will be here. So you could also do the integration from here, and using the initial condition to be 25, you would be able to obtain this green function. So in here, after you have decelerate, so yeah, starting from 25, you would decelerate down at a linear rate, and then you will reach 0 after the deceleration. And so after you have figured this out, you want to hope that during the time equals to something here, your velocity will be 0. So if you actually do the integration, you would be able to obtain this function. So it is moving higher and higher. So let's see here, you are moving at 25 meters per second within a certain time, and then during this time you start to decelerate, and hoping that your maximal point would be lower than 60. So you could see here that you could actually decelerate below 60 if you go at 10 meters per second squared, but then if you reach a point of about 5 point something, you would you would actually crash into the obstacle. And and yeah, we could we could check the answer to be correct. So if we put 6 if you if we put 125 over 24, this is the exact point in which you will hit 60, which is about 5.2083333. So, so in here you could see there are some parameters that I used, and feel free to try it on your own and try to model your own problems in your own problem sets. So that's all for today, and I hope this will actually help you to understand this concept much more better. And if there is any questions regarding the simulation or the topic, feel free to leave it in the comment. So thank you very much, and I will see you guys on the next episode.